Series, we are interested in talking about two variables at once. And one of the ways in which we can express the relationship between two variables at once, at one time, is via a graph. But before we even go there, let's just think about what it means to have two variables and why we would want to do that. So here's this little handy-dandy applet which you have access to on our weekly module. And in this little applet, this little crab moves back and forth. So I will go ahead and press the play button. And I encourage you to play with this to get the hang of it. So there's this little crab moving along, kind of this ruler type of thing. He speeds up a little bit, and then he stays still. So this is basically a repetition over and over again. So suppose we wanted to just keep track of one of the variables involved in this process, which is time. Time is a factor that determines how far this crab has moved. So what I'm going to do is I'm going to pause this and I'm going to restart the time, and I'm going to press this little time button, and here's this little finger that along this line is going to keep track of time. So keep in mind that it's going to move at a constant pace because time moves at a constant pace. So time doesn't move fast or slow down, it moves at the same rate despite how we feel sometimes. So as I press play, this finger is just keeping track of how many seconds have passed. Notice that the axis is unlabeled. Notice that it doesn't slow down or stop as the crab slows down or speeds up and comes to a complete stop, because this is keeping track of time. So imagine this being 0 seconds and this being, well, however many seconds this is, which is probably about, what, maybe 5 or 6 seconds. And now let me go ahead and undo time, and now let's just go ahead and keep track of the crab's distance. But we're not going to do it along this line because this line represents time. We're going to let the crab move along this line. So now we will take into account, now we basically are using a finger to keep track of exactly where this crab is. So now we're going to plot along this line, or keep track of with this finger, the distance that the crab is from the starting point. So I'm going to press play, and notice that this finger should speed up really fast, and now it should stop because the change in distance is 0. The crab isn't changing anymore after a certain period of time. So that one stops. Okay, well, ideally what we would like to do is to relate these two things. We would like to relate the crab's distance away from the starting point of 0 as time passes by. So now let's pause this. We'll restart it. We're going to keep track of two fingers now. One finger is still going to move along this axis, and I encourage you to try this and see how actually challenging it is to think graphically, because now these two fingers are going to keep track of, one is time, and notice time is going at a constant rate as it was before, but now this finger speeds up and slows down to keep track of where the crab is. So our reasoning, or the takeaway from this, is that we want to keep track of both of these quantities at one time. So what do? Well, we're going to allow this to sprinkle some fairy dust. So we're going to reset the time, and as it moves, we're going to look at the intersection, the this way intersection and the this way intersection of those two fingers. So you'll see what I mean in just a second here. So I'll press play, and now notice that there is this line being formed at where both this dot and this dot are. So essentially this is plotting a bunch of ordered pairs, a bunch of points at one time. And so even though time is still moving, as time passes, from here on, the distance stays the same. It doesn't go up or down. This is often what we refer to as an increasing function, because as the input increases, so does the output, at least up until here. So up until here, we have what's called an increasing function. And then from here to here, we have what's called a constant function, where the output is not changing. This finger stays the same. Anytime this finger is moving, well, if it were moving down, we would have a decreasing function. So let's reset this and let's take a look at another path. Okay, so the crab is going to do a different path, but we're still going to keep track of the same thing. So first we'll do time, which time doesn't change, right? Time is not affected by anything. I'm going to remove the fairy dust, and we're going to start over. Or we're going to try to start over. Second path, we can also demonstrate sort of the same idea by considering just time and using the time finger to keep track of how much time has passed. basically we could close our eyes, move our finger, and it has nothing to do with the crab's distance. But of course, we could also keep track of distance from start. So of course, this finger is moving relative to how far this crab has moved. Now if you try doing this with your two fingers, you'll find out pretty quickly that it's not as easy to do as it appears to be. And of course, if we combine those two fingers, now we have a point that's being formed by the intersection of moving across and moving up, which is how we've come to know and love this idea of ordered pairs. And of course, if we sprinkle our fairy dust, we get the shape of the graph. So we have an increasing graph, but then as the input increases from here to here, we notice that the graph decreases. So we would call this a decreasing portion of the graph from this time right here up until this time. And what do you think we call this right here? That's the constant portion, because as you notice, the distance finger doesn't change. The crab is standing still at a distance of 0. So this is some of the covariational thinking, or this is called covariation, because we're co-varying something. We're changing something together, and we're observing how two things change together. And that's essentially what we get when we put together two number lines and then look at a point as being the simultaneous intersection of two values at one point in time. To summarize the question, why do we consider two variables at once? The possible answer is to understand how changes in one variable affect changes in the other variable. So take time and the distance of the crab. We want to understand how time affects the crab's distance. Maybe we don't really care that much in this particular example, but that's generally what we want. So let's just say we want to study two variables, and this is one that's probably part of our everyday lives. The cost to fill up your gas tank, let's say that's one of your variables, and number of gallons purchased. So we want to understand how those two things co-vary. Well, first of all, let's identify input-output, or independent-dependent. So remember, the output is the dependent because it depends on the input, and the input doesn't depend on the output, so it's independent. So what do you think, which do you think is which? Do you think cost depends on the number of gallons you purchase, or do you think that the number of gallons purchased depends on the cost to fill up your tank? Well, most likely, I mean, you can make an argument either way, and honestly, it can go both ways. That depending on what you want to determine, your output is the thing that you want to basically be able to project based on different values of the input. Well, what's more likely? Do you think we want to project the cost to fill up your tank, or do you think we want to project the number of gallons purchased? I think it probably makes sense to think about cost as the dependent variable and the number of gallons as the independent variable. Now you can say, well, I can only afford so much, so to me it's going to depend on what the total cost is, and then I'll purchase the number of gallons based on that. But we're really talking about filling up your tank here. So that depends on the number of gallons you purchase. Okay, so that allows us to say that the cost is a function of, I'll just abbreviate this, AFO is a function of number of gallons. Remember, that's how we always state it. The output is a function of the input. That's something to get used to because it's something we hear so frequently. So we could say cost, let that be represented by C, let gallons be represented by G, is represented by an equal sign, a function of is kind of the F parenthesis notation, and cost is the output, G, gallons is the input. So let's suppose that gas, 1 gallon is, we'll just say for simplicity, $3. So gas takes a drop in price, and you're happy because it's only $3 a gallon and not $3.50 a gallon. And so now we can probably try to understand the relationship between gallons and cost. Okay, so I'm going to create a little table here. So if I purchase 0 gallons, I don't pay anything. If I purchase 1 gallon, well, 1 goes with $3. 2 gallons, well, that's doubling the cost as well, so that would be $6. By the way, notice that these two things are equal, that the rate is the same, so 2 would cost me 6, 3 would be... And so for every additional gallon that we purchase, we notice that the cost does go up by $3. Okay, so we can continue going on in this pattern, And of course, we could probably write a pretty solid formula for this. It appears that every time our gallons increases by 1, cost increases by 3. And so if you take the number of gallons and you multiply it by 3, you seem to get the cost. So if I take the number of gallons, G, and I multiply the number of gallons by 3, now remember, gallons is a variable because it can be any one of these values or anything beyond that, or anything in between as well. And if I multiply $3 per gallon times the number of gallons, I get the total cost. So there's my formula for it. And of course I could plot these points too. So when we graph points, as you probably learned before, we have two axes, and one of them is usually the input axis. And in this case, my input is G, which stands for gallons of gas. And up here I have my output, or my dependent variable, which is represented by C for cost. So we're not going to focus too much on making very pretty lines here, but remember we want to make them equally spaced, and cost will go up by 3 evenly each time. So 3, 6, 9, 12, and 1, 2, 3, 4, 5. And so we would begin plotting our points, and we can kind of see pretty quickly that, again, this covariation, that as gallons increases, we expect the cost to go up. And not only in any way, but it seems to go up in a straight line fashion. It goes up linearly. So regardless of how much the cost is, or how many gallons we get, we seem to be incrementing by the same amount. So over 1, up 3, over 1, up 3, over 1, up 3, over 1, up 3, and so in continuation of this process over and over and over again. So typically we're going to let our calculator do a lot of the graphing for us, but this is just to get us thinking in terms of covariation. Maybe we couldn't see all these things, using your finger tool and moving along gallons. You could probably pretty easily show that if you move your finger this way, then this should move at about 3 times as fast in this direction, right? Because for every 1 you move this way, you should have gone up 3 this way. So the covariation idea applies here, even though it's not a crab moving and we're not keeping track of time. Let's take a look at a sketch of an example. So suppose we have the number of fires in a forest, and we're modeling that as a function of inches of rainfall. I should say of, not or. With very little rain, there are many forest fires. So that's all we really know. Okay, so first of all, let's identify what our dependent and independent variable are, or output and input. So we have 2 of them, and it's number of fires as a function of inches of rainfall. Okay, well, we know that output is a function of input. That's the way it's always written. So this must be my output variable, or dependent, and this must be my input variable, or independent. Okay, so I'm going to just sort of sketch a graph based on the very little information I have here. And so I'm going to look at the inches of rainfall, and that's going to be measured in inches. So typically we do put our units there so we know exactly what kind of measurement we have. And then here we have fires, and this is just measuring the number of fires. That's the characteristic that we're keeping track of. And all we know is that with very little rain, there are many forest fires. Okay, well, if there's very little rain, like let's say 0 inches, so here's 0, 1, 2, 3. We could draw our tick marks if we wanted to. For very little rain, we have a lot of forest fires. So I don't know exactly what a lot is, but I'm going to put that up here, because that represents, with very little rain, there are many forest fires. Well, what's going to happen as the amount of rainfall increases? Well, it's going to probably, the number of fires is going to go down in some way. So we don't know exactly how that would look. Maybe after 2 inches, you get a bigger drop off. So it kind of looks like maybe like this. We don't exactly know, but we would have a decreasing function, because as the input increases, the output seems to decrease. So that's with more rainfall, we have fewer forest fires. Another example we'll consider here is, let's just say we have some raw data. Now this is actually taken from the U.S. Statistical Abstract, and they report data every year. It's part of the Census Bureau, and they took a look at, from the years 2004 to 2010, the amount of solar energy being generated or being used. So this solar unit is measured in what we call quadrillion BTUs. Now that's bigger than a million, billion, trillion, quadrillion. That's a lot of energy, and BTU stands for British Thermal Units, which is a way of measuring this sort of energy output. So we notice that there is an increase in solar, and we can see that just by the table, right, as the years increase from 2004 to 2010. We also see that the amount of solar energy being generated seems to be increasing up from 6 to 10, 0.06 to 0.10 quadrillion BTUs. Now it's not doing it at regular rates. For 3 years we noticed that the rate hasn't really changed, but that there's really no change in the generation of solar, but over the following 4 years there seems to be kind of this upward trend. Well, we can see that better in a graph if we were to individually plot the points. And here we have the year, and here we have the quadrillion BTUs of solar power. Now right now we don't have a way of making forecasts. We can of course say that in 2010 it was about 0.09, and we can probably make a pretty good estimate of what it'll be the following year, but let's say we wanted to be a little bit more precise. So this is a tool we'll pick up later on, but what we would generally do is build a mathematical model. We would actually create an equation, and this method is known as regression or trending. So we're going to select linear right now for reasons we'll talk about later. And we get this beautiful little equation that tells us that y, that in this case it's generically calling the power y, and it's calling the year x. So it's telling us that we can figure out what y is, or estimate it, based on knowing what year we're talking about. Okay, so if we wanted to make a prediction for 2011, now notice that these points don't fall along this line, but the line kind of seems to wrap around those points, or the points seem to kind of very closely wrap around it. So in this case our model would be, our mathematical model, which is just really our way of saying equation, would be 0.0071. I'm going to write this down. So I'm going to use S for solar equals 0.0071, and I'm going to use T to represent time. So I'm going to use S and T, and that's minus 14.191. Now of course we'll analyze this more later on, but we know that that solar output is a function of time, right? Because the input is time, so that means when I use this function, this equation, to process the year, I should get on the output side, I should get the amount of solar power. So let's say we wanted to estimate something like f of 2013 based on this data. Well, we could do that, and that would just be as simple as putting in 2013 for the year minus 14.91. Now again, I want to emphasize that this is not multiplication right here. This is saying that a function of the year 2013 should output an amount of solar energy generation. So we can now come over here to our calculator. Now this one does mean multiplication, right? It's kind of confusing at first. The f of just tells us what the input is that we're going to process on the right-hand side of this equation. 0.0071 times 2013, and definitely we could just use the multiplication sign if we want, minus 14.91, and we get, in this case, did I mistype something here? Well, let's see. Let's try to figure out what happened. I see what happened here. We should have a 14.191, not 14.91. That can make a big difference. So I'm going to come back to my calculator. A neat little trick. If you press second and the enter button, that pulls up your last entry, so that all I have to do is go back and overwrite just the portion that I want to change. And this tells me that I would expect about 0.1013 quadrillion BTUs to be generated, because my input is year, my output is BTUs. So input is year, output is BTUs. So if I put in 2013 for my input, my output becomes 0.1013. Now this may not mean much to you because you're probably not used to thinking in quadrillion BTUs, but this is a way of using a mathematical model in order to make projections into the future, and this is a very safe and sound way most of the time to do so. As a capstone to this little video series, let's answer one more question now that we're working with graphs a little bit. So how do we determine whether a relationship is a function if we're looking at something graphically? Well, let's pick a couple of each. So I'm going to generically call these x and y for input and output, and I'm going to write down a few non-repeating inputs, 1, 2, 3, 4. So already we know that based on these ordered pairs that this is going to be a function, because for every input value, for the input value of 1, there's no other 1 in here, there's only one associated output value. Same thing for 2, same thing for 3, same thing for 4. So we would expect this to be a function, and let's see what it looks like. So I plot my x along the input, my y along the output, 1, 2, 3, 4, and roughly 1, 2, 3, 4, 5, 6. So when the input is 1, the output is 6. When the input is 2, the output is 7. When the input is 3, the output is 4. And when the input is 4, the output is 5. So it kind of looks somewhat like this if we were to give it some connectivity. So we have an increasing component, and we have a decreasing component, and then we have an increasing component. So now we want to say, well, okay, that doesn't really give us a whole lot of insight, but let's pick something that does, that we know is not a function. So this does lend some insight. We didn't just do this for no good reason, but we'll look at both cases and we'll see kind of what stands out. So let's just say that all of these x values were 2, and each 2 had a different associated output value. So 4, 6, 7, 5. And so we were to plot this. Of course, we only need to go out to 2 along the x, and then 1, 2, 3, 4, 5, 6, 7. Well, when x is 2, y is 4. When x is 2, y is 6. When x is 2, y is 7. And when x is 2, y is 5. So if I were to connect all these dots, notice that I get a vertical line. Now we know that this is not a function because for one output there are multiple, for one input there are multiple outputs. So this is not a function, and this is a function. And you notice that the difference is that if I slice a vertical line through any point along this graph, in particular when x equals 2, I cross through multiple points. Now if I cross through multiple points, that means that for that input I have multiple outputs. Hence, we don't have a function. Now if I take a horizontal line and I slice it anywhere through this graph, notice that it only cuts through once. Now you've got to be careful not to draw it diagonally. It has to be a perfect up and down line. But you notice that at every point there's only one intersection of the vertical line with the sketch that we have down here. So this led to probably what you maybe have heard of before called the vertical line test. A vertical line test. And essentially it's a graphical tool that says that if a vertical line can be drawn anywhere on a graph, and the line intersects the supposed function, the thing that we're trying to determine whether it's a function, and intersects the supposed function at only one point, it is a function. So that's the beauty of this vertical line test. So if we draw something, we can probably pretty quickly tell. So let's just say I draw this. Now I'm calling that a function. Well, you can probably see pretty quickly that I can almost anywhere draw a vertical line and it intersects this curve at least 2 or 3 times. So this would not be a function. And that will kind of serve as a capstone to this video sequence. This is a quick tool, but don't forget why this works. We kind of developed it intuitively from the beginning, and then we said, let's call this the vertical line test. If I can draw a vertical line through it and only touch at one point, it must be a function.